A Hamilton path is the path that passes through each vertex of a graph exactly once and only once. If a Hamilton path begins and ends with the same vertex, then it is called a Hamilton circuit. We have the graph here. It has many Hamilton paths, and one of them is A, B, C, D, E. So we're going to start at A and visit B, then C, then D, and then E. So the red path we have is a Hamilton path. Now, if we want to make the same path as a circuit, we just have to connect E with A to make it as a circuit. Also, this graph has many Hamilton circuits, but one of them is A, B, C, D, E, and A. So now, the new red circuit we have is a Hamilton circuit. We have another graph, and we can trace here a Hamilton circuit. So we're going to start at R, and we're going to visit each vertex once and only once. You don't have to cover all the edges because we have a Hamilton circuit, not an Euler circuit here. So we're just interested in covering all the vertices once and only once. And we're going to start where we began at R because we have a Hamilton path. If we stopped at S, it would be a Hamilton path. But since we're talking about a Hamilton circuit, we're going to go back to R, where we started. Another example of a Hamilton circuit. A complete graph is a graph that has an edge between each pair of its vertices. So this is very important. So a complete graph is a graph that has an edge between each pair of its vertices. We're going to see a few examples. We're going to see a few examples like a complete graph between two vertices, 3, 4, and we're going to increase the number of vertices. The number of Hamilton circuits in a complete graph with n vertices is n minus 1 factorial. So what do we mean by factorial? And we can find factorial using the calculator. 1 factorial is 1, 2 factorial is 2 times 1, that's 2, 3 factorial is 3 times 2 times 1, 4 factorial is 4 times 3 times 2 times 1, and keep in mind 0 factorial is 1, so if a graph has 10 vertices, how many Hamilton circuits does it have? First of all, the graph has to be a complete graph. Keep in mind the vertex in the middle, that's not a vertex, only the blue one are the vertices. So we have a complete graph that has 10 vertices, so n here is 10. Therefore, the number of Hamilton circuits is n minus 1 factorial, that's 9 factorial, which is 362,880 Hamilton circuits. We have a complete graph with 4 vertices, therefore it has 6 Hamilton circuits. Now it has 6 starting at A, and it has the same one starting from B, and it has the same one starting from C. It's just the order of the letters will change from the starting and ending vertex. So it has 6 Hamilton circuits, but I can draw these 6 from A, or from B, or from C, or from D. So it doesn't have 24. It has only 6. It's only the order of letters changes. It depends on the starting and ending vertex. Now we chose A, our starting and ending vertex. So these are the 6 Hamilton circuits, and let's see what they are. So the first one, now the second one, now the third one, now the fourth one, now the fifth one, and then the last one. So these are the 6 Hamilton circuits. Weighted graph. So weighted graph is a graph where the edges has numbers, and these numbers can be prices, they can be cost of trips, they can be distance, or they can be numbers, just numbers, and we call them weights of the edges. For example, if we took this Hamilton circuit A, B, D, C, A, and I'm trying to find the cost of that Hamilton circuit, first the cost from A to B is 100, then the cost from B to D is 154, and the cost from D to C is 170, and the cost from C to A is 137. Therefore, the total cost of my Hamilton circuit is going to be 561. So we're going to add all the sums we have. The brute force method, you need to consider all the Hamilton circuits with their cost, and we're going to take the minimum optimal solution here. We're interested always in the cheapest total cost or in the lowest total cost. So we're going to take the minimum sum of the weights, but we have to consider all the possibilities, and then we're going to take the minimum sum. So for example, if we took the same graph we have, so we agreed that it has 6 Hamilton circuits, so we find the cost of each Hamilton circuit, and we notice that we have 2 minimum cost. Therefore, we have 2 Hamilton circuits with minimum cost of 500. The nearest neighbor method, we need to model the problem with a complete weighted graph, and we're going to start on a vertex as our starting point, and we're going to choose from that vertex the smallest weight. Then when we land on the second vertex, we're going to choose the edge with the smallest weight, and so on until we return to the starting point. We have a manager who lives in city A, and he's required to travel to regional locations in cities B, C, D, and E. The weighted graph shows give the one-way airfares. We need to use the nearest neighbor method to find an approximate solution. What is the total cost? First, we're going to decide on a starting point, and we're starting from A. Now, from A, we have 4 choices, but we're going to choose the smallest one. Now, from C, we have also 3 choices. So the 3 choices we have from C, and we're going to choose again the smallest one. Now, from E, we have 3 choices. Now we can choose this one because it's going to take me back to A, and I haven't revisited B and D. If I have to choose between this one and this one, definitely we're going to choose the 194 because that's smaller than 195. Now from D, we have three choices again. We have this one, we have this one, and we have this one. I can't choose this one because it's going to take me back to C and I haven't revisited B, and I can't choose this one because it's going to take me back to A and I haven't revisited B. Therefore, now we revisited all the vertices once. We have to go back to A, so the only choice we have is the 180. Therefore, using the nearest neighbor method, we're gonna add all the weights of the edges visited, and this is the total cost of our trip. So that's a Hamilton circuit starting from A and ending at A, and the cost of this Hamilton circuit is $748.